Hello, I'm Akila.
Hello, I'm Ennis.
I am Josh.
I'm Rakul.
I'm Leo.
Our proposed research question is, how does the immune response to SARS-CoV-2 predict clinical severity of COVID-19 patients?
Current data suggests that around 20% of COVID-19 patients experience more severe disease. But what differs in the immune response that results in a proportion of patients progressing to a more severe state? To answer this question, we can categorize the immune response into different stages to better reflect the clinical progression observed.
Well, what do we know? So SARS-CoV-2 is 80% similar to SARS-CoV and 50% similar to MERS-CoV. The knowledge of such similarities has influenced our study of the immune response to SARS-CoV-2.
SARS-CoV uses a third of its genome, namely the accessory genome, to cause inflammation, antagonize the interferon response, and evade the immune response alongside other functions.
We have compiled the data from various studies investigating the immunological characteristics in both mild and severe COVID-19. Our ultimate aim would be to identify and derive risk factors and biomarkers indicative of disease severity, thereby providing a prognosis and potential management of the disease.
Now on to the methodology. With regards to our inclusion criteria, we selected papers with studies that focus on the clinical characteristics of COVID-19 with severity as a comparator and immune system biomarkers as a potential measure of severity. We focused on primary datasets from the recent pandemic as of December 2019, mostly in the form of retrospective cohort studies.
Now, our exclusion criteria. We omitted studies without clinical significance. Given the recency of the data, we also excluded papers with sample size of less than 10 COVID-19 patients.
We selected our papers based on how well the immune response correlated with disease severity.
We extracted 9 key findings based on our 5 selected papers. Finding 1, age and gender were significant risk factors associated with death from COVID-19. The presence of a comorbidity was also an independent risk factor.
The second key finding is that patients with a severe presentation of COVID-19 in ICU were shown to have impaired viral clearance relative to non-ICU patients. From this graph, we can clearly see that the time taken for upper respiratory tract samples to become PCR negative for the virus is significantly longer for ICU patients than non-ICU patients. This finding was obtained by recording the proportion of PCR positive patients every day after the onset of symptoms in the ICU and non-ICU groups.
We found a significant reduction in the subsets of T cells in COVID-19 patients, namely CD4 and CD8 positive cells, when comparing severe disease to moderate and mild.
Importantly, multivariate analysis showed that this lymphocytopenia significantly and negatively correlated with inflammatory markers, including erythrocyte sedimentation rate, C-reactive protein, and interleukin-6. This is illustrated in the scatter graph of Figure 3, where both CD4 and CD8 positive T cells decreased as ESR, CRP, and IL-6 increased.
As our fifth finding, we found that B cells were currently not a useful correlate to indicate disease severity. Contradictions among papers make it harder to draw conclusions on the use of B cells as a biomarker. Therefore, sample sizes of future studies must be increased.
Additionally, a retrospective study of 21 patients hospitalized with COVID-19 found that the percentage of CD4 positive T cells expressing interferon gamma were significantly reduced in severe patients relative to moderate patients. A similar study with 522 patients found that levels of TNF-alpha, IL-6, and IL-10 were significantly higher in ICU patients compared to non-ICU patients, as demonstrated in the dot plot in Figure 4a. Furthermore, fluorescence-activated cell sorting analysis in 14 patients found the expression of exhaustion markers were expressed at increased levels on T cell subsets in ICU patients relative to non-ICU patients and healthy controls. This relationship is depicted in the dot plot in Figure 4b.
Our eighth findings showed that the mean serum IL-6 concentration was significantly higher in severe cases compared to moderate cases. And finally, patients with severe COVID-19 more frequently reported dyspnea as a symptom when compared to moderate cases.
Now, on to the discussion. What are the risk factors to a more severe COVID-19? For one, older age is linked to severity with a higher mortality in over 60s. Immunosenescence and aging microenvironment of the lungs impair dendritic cell presentation of viral antigens to T cells. Secondly, males are more likely to experience a more severe COVID-19. A number of critical immune genes are located on the X chromosome, in particular the gene for TLR7. This protein isn't inactivated on many female immune cells, so the immune response is more effective in females. One major factor to consider is ethnicity, as a third of patients admitted to intensive care were from BAME groups. Although there is great literature on this, none are peer-reviewed, so one cannot conclude the significance of ethnicity. Observational studies have shown a correlation with low serum levels of vitamin D in BAME groups and the incidence of ARTIs. Secondly, it has been shown that countries with a BCG vaccination policy have a reduced morbidity and mortality from COVID-19 due to its non-specific immunity. Finally, the presence of comorbidities creates a pro-inflammatory metabolic state which causes an enhanced release of cytokines and functional deficits in innate and adaptive immune cells. In obese patients, type 1 interferon responses are attenuated.
Okay, so how may SARS-CoV-2 evade the immune response, and does this ability affect COVID-19 severity? Well, in the initial phase of a coronavirus infection, host cells detect PAMPs and elicit an effective innate immune response to prevent uncontrolled viral replication and dissemination. This is driven significantly by the rapid expression of type 1 interferons and the downstream signaling cascades they trigger, culminating in the reprogramming of host cells into an antiviral state. For the novel human coronaviruses, SARS-CoV and MERS-CoV, this interferon response is suppressed. Studies have shown that SARS-CoV is capable of interfering with interferon type 1 induction and signaling by multiple strategies. Given the similarity between SARS-CoV-2 and SARS-CoV, SARS-CoV-2 may employ those same anti-interferon immune evasion strategies. A diagrammatic representation can be seen on this slide. These parallels ought to be drawn in a speculative manner, and there may be further mechanisms utilized by SARS-CoV-2. The proposed innate immune evasion strategies for SARS-CoV-2 and the consequences may in part explain the significantly elevated systemic inflammatory proteins, the neutrophilia, and the lymphopenia, all associated with COVID-19 severity. The suppression of the type 1 interferon response leads to enhanced viral replication and so increased viral load, accompanied by an increase in inflammatory cell death, pyroptosis, the products of which provoke the aberrant excessive inflammatory response via immune cell recruitment. Also, Chen Ji et al. Suggests that COVID-19 severity is linked with the suppression of interferon gamma production by CD4 positive T cells, which is an important cytokine for the resistance against viral infection.
Now, let's dissect the immune response further. Following on from the virally driven pyroptosis previously mentioned, T cells and macrophages are recruited to the site of infection via the release of IL-6 and CCL2, reported to be increased in COVID-19 patients. This is represented diagrammatically above. Consequently, an autoinflammatory loop is established, as illustrated on the slide. Briefly, the feed-forward loop where the recruited CD8 positive T cells in turn activate cells of the innate immune system subsequently contributes to the hypercytokinemia observed. Crucially, if you clear the virus, this loop is disrupted and resolution and immune regulation should ensue. In at-risk patients, however, despite the activated T cells containing cytotoxic granules, fail to clear the virus. As a result, hyperfunctional CD4 positive T cells are recruited and lead to a macrophage activation syndrome by the release of interferon gamma and IL-2. This hyperfunctional state of the immune system agrees with the decrease in regulatory T cells observed in several studies. This impaired viral clearance allows perpetuation of the autoinflammatory loop. This results in an excessive release of cytokines, notably TNF-alpha, IL-10, and IL-6 from immune cells, and may be mechanistically linked to the increased expression of exhaustion markers such as PD-1 on the surface of T cells. T cell exhaustion means that T cell effector function is ineffective. Thus, the virally driven hyperinflammation continues, leading to an aberrant release of pro-inflammatory cytokines. This culminates in a cytokine release syndrome, which may result in multi-organ damage. This clinical progression outline has wide-reaching implications. Firstly, it explains the immunopathology observed in severe patients and why those with aberrant immune responses are more likely to progress to more severe stages. Furthermore, by understanding the mechanisms of immunopathology, we can not only develop more targeted therapies, but use the T cell and cytokine profiles of the patient to better direct and optimize the timing of such interventions. For example, anti-PD-1 antibodies may be efficacious in patients where T cell exhaustion is evident.
So finding 3 has shown us that the immune response leads to a lymphopenia. The decrease, particularly in CD4 and CD8 cells, can be used as a biomarker to predict the severity of disease and therefore its potential management. We don't believe B cells are as good a predictor. Lymphopenia is particularly significant in severe disease compared to mild disease, leading to a lymphocytic dysfunction. This can be used and explained by various mechanisms. A couple examples include the virus destroying immune cells and there is damage to immune cells caused by inflammatory mediators. So why use lymphopenia as a biomarker? Ten et al. Proposed the use of a lymphocyte percentage time model to determine disease severity. You categorize the patient using the lymphocyte percentage over time, like shown, and identify any alterations which can be used to decide whether to put the patient into ICU or not. This modeling was verified for consistency with the Cohen's kappa statistic. This classification system for disease severity is important for preventing overall undertreatment. This could work alongside pulmonary imaging as a basis for classification, which Leo will talk about.
Now, about the clinical manifestations of the cytokine storm. Alongside lymphopenia, the resulting cytokine storm induces significant interstitial lung inflammation, which culminates in viral pneumonia. This lung damage, visualized on a chest CT scan, seems to resolve itself in moderate cases, but worsens in severe cases. Since a high serum level of IL-6 is associated with severe COVID-19, the immunomodulatory effects of tocilizumab, an anti-IL-6 receptor monoclonal antibody, could control the CRS, hence reducing mortality. Without timely intervention, pneumonia can precipitate complications, particularly ARDS and MOD. Consequently, supplemental oxygen therapy is required to combat the hypoxemia, which aims to restore optimum SpO2 and improve survival. This suggests that dyspnea may be utilized as a prognostic marker to recognize respiratory failure, and thus delivering early supportive care to these at-risk patients would significantly reduce mortality. However, in a delayed ARDS diagnosis, the vast respiratory damage from continuous hypoxemia means that extracorporeal membrane oxygenation or even mechanical ventilation could be required.
So, to summarize, we've identified the risk factors and biomarkers that can potentially be used to monitor disease severity. This could be used to indicate suitable time points of intervention.
By delineating paths of immune response, we provide clinicians with a theoretical framework to use more appropriately timed and targeted interventions with respect to the immune status of the patient. Further research into the role of B cells, for example, may give further insight into how we can use more efficacious immunomodulatory agents.
We have identified limitations in our research, like heterogeneity in study design, for example, the definition of severe disease.
And most of the knowledge on the characteristics of SARS-CoV-2 is based on extrapolation from that of the previous novel coronaviruses. Hence, this poses a limitation in our study, as the potential mechanisms used by the virus can only be used tentatively to explain our results.
And finally, we could use our studies better by using a weighting system and avoiding a selection bias. Here is our entire conclusion. Thank you for listening. And these are the references.